So one thing that people saw when uh, that gave them rise to like there must be something more to just atoms being there was something like this: the idea of chemiluminescence. Chemiluminescence is basically the idea that chemicals, when they react, some of them give off light, and that light can be of different colors. And the first suspect of why these colors are the way they are, was that there must be something happening with the electrons, because after people figure out that electrons are there and they're outside the electrons, outside the nucleus, and they are responsible for most of the things that they do. So they were the first primary suspect of this kind of thing. But why exactly would they do that, and how exactly would they do that? That will take a long time for scientists to actually figure out. Now, the idea is that ionization energy gives us some clue. The different values in there, they show something happening much easier or with very less energy in one atom, while happening at a very high energy in the second atom. So even though you are removing the same electron, and atoms are roughly the same size, but the other one is taking 519, which is like just giving it away for no particular reason. But for the other one, like helium, you really see get that. And not just that, there were more patterns in there yesterday. Yeah. So we said that these levels are there. And then these were the energies that people had. So now, to identify what levels there are, we said that the first electron or energy is actually for the outermost electron. So that's not the first electron, it's actually the last electron that you're removing, which is why it was so easy to remove. And these four factors were the ones that scientists shortlisted. They said these are the four things that are responsible for why ionization energy values increase the way they do. One was distance, that if the atom is bigger, obviously it will take more energy to remove. Like if it is bigger, it will take less energy because the electron is further away. And if it is closer, the attraction is stronger, so it takes more energy. Then nuclear charge. Nuclear charge again is about the charge on the nucleus that pulls on the electron. So the more the charge, more the attraction. So no wonder if you go from left to right in the period, people saw that you had to supply more energy, even if you were removing the very first electron. Then the shielding effect. Shielding effect was that the inner electrons repel the outer electron. They don't allow it to come closer to the nucleus. They kind of shield the nucleus. And that is what the shielding effect is. They shield the nucleus from the outer electrons in a bit to repel them. And then we had the pair repulsion that we will discuss later on. But so far, these were the factors that we have. Now, what trends do we have in the size of the atoms? Obviously, nuclear charge affects the size. So if you have more nucleons or more protons for an atom of roughly the same size, obviously the size is going to be affected. You take two atoms, both of them are the same size, and one atom has more protons than the other. Naturally, the size is going to reduce because it's going to pull on electrons. And actually, from left to right, the size decreases. And that is because protons are more, but shell is the same. So from left to right, that's the very first trend that they figured out, that from left to right, size decreases. Why? What is not changing? The shell number. Shell number or period number is constant, which means shielding is constant. Why? Because shielding is inner electrons repelling the outer electrons. So shielding doesn't really matter if you're talking about the same period, but the proton number is increasing. So when proton number increases, nuclear charge increases. And when nuclear charge increases, attraction increases. And when attraction increases, size decreases. So identifying this factor was important in knowing why, when you go from left to right in the periodic table, things are getting more and more energy. So that was one thing that they figured out. Yep.
Size of what decreases?
I'm sorry?
The what decreases from left to right? Doesn't the size of the atom?
Decreases. The size decreases.
So doesn't the size of the atom increase from left to right in the periodic table?
Yeah, so that's what I'm saying. The size decreases from left to right.
No, sir, doesn't it increase?
Why would it increase? Think about it. You have the same period, but you're adding more and more protons.
Yeah,
Why would it increase?
because
They
you're
should pull it.
adding.
You're adding more protons, which means you're pulling the outer electrons more. It's the same shell. Let's take the third shell. So in third period, you have three shells. The last shell decides the size, and you have electrons on the last level, whatever it is, and they're being pulled by 11 protons for sodium, but 18 protons for argon. No wonder argon is smaller than sodium.
Like the size of the electron cloud or just the size
Yeah,
of
the
the atom?
cloud. The
Okay.
size of the atom and the size of the electron cloud is the same thing. That was one of the key identification or the patterns that they saw. Similarly, from up to down, like downwards, so from top to bottom, they saw that the size increases. And that's pretty simple. Size increases because the shell number increases, period number increases. So more shells. And that means shielding increases. So not only are there more shells, they're being pushed outwards as well. So size increases. But what about nuclear charge? Nuclear charge also increases, but it's not that significant because the size increases by a much bigger factor than the nuclear charge. So nuclear charge increases, which must offset the effect, but it doesn't because it's not increasing by that much. So size doesn't increase that much. Okay, so the dominant factor from left to right is the nuclear charge, but from top to bottom, the dominant factor is the shielding. And that is how they saw two main trends in the way things were arranged. And that gave us some idea of why, when you're going from, for example, lithium and then sodium, then potassium, the ionization energy was decreasing. Ionization energy was decreasing. It was easier to remove those electrons because, yeah, from top to bottom, the electrons are in outer levels. The levels are increasing. So naturally, they are easier to remove. And across the period, they were getting difficult and difficult to remove because across the period, what was happening was that the nuclear charge was much more significantly increasing, which means they were pulling on the last shell more. So it was difficult to remove. So let's go back to this table. This table is all we need to know the electronic structure or the configuration. So let's look at something that is in the same period. Lithium, beryllium, boron, carbon, they're all in the same period. So you can see that the general trend, again, the general trend is important here. I'm not getting into the specifics here, but the general trend is that the value increases. So, for example, if you look over here, let me highlight them. So, this increases. There's a slight decrease, but then overall it increases, bounces back, increases, again, slight decrease, increases. And suddenly this is decreasing at the end. So, this is all in the same period. And in the period, the general trend is that it's increasing, which means that actually the size of the atom is decreasing. So it's difficult to remove them. So the general trend across a period, they found out that it was easier to remove them. So they assumed that actually the level is the same, but the size is smaller. So the energy level from which you're removing them is the same. So that gave to the idea that, all right, this level is actually the same one, which means that the first two, they're in the same level. The next eight, they're in the same level. And obviously with sodium, it goes on. So they figured out that, all right, in the first period, we have the first shell or energy level. Second period is the second shell. And that gave the reason for them to understand that, all right, shell number is related to the period number. But then, is the first shell bigger or is the second shell bigger? For that, they figured out that, all right, let's look at the value. So the first shell value is this one, and the second shell value is this one, and the third shell value is this one. I'm removing the very first electron. What does that mean? That means that first shell is actually smaller, closer to the nucleus. Second shell, further away from the nucleus. Third shell even further away, because it's getting easier and easier to remove as you go from one shell to another, which means first period shows the smallest atoms. Second period goes the next bigger ones. Third period goes for the next bigger ones, which shows that as you go from top to bottom, the size increases, and that matches this observation as well. All right. So that is how they figured out that, all right, from first to seventh, when the shell increases, the size increases, the electron goes further away. So within the same shell, shielding is more. So it's the general trend is it's closer, and the general trend is that the size is smaller, which means it's difficult to remove them. All right. So that's a general trend. Now they were like, wait a minute. There are still some changes that we can't really explain. For example, why is it that we are removing the very first shell from the very first outer shell, and from lithium to beryllium, it's increasing, but suddenly from beryllium to boron, it's just decreasing. So it increases, decreases, that increases, 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 decreases, and then increases, then increases. So this decrease we can identify. This is because you have jumped to the next level. The atom is much bigger now, much easier to remove. But these were very difficult to explain. Like, why? Why is it that after the first two, suddenly we have a decrease? Then after three, there is another decrease. And then after three, there is another decrease. And they saw the pattern repeating. They saw that after two, they decreased. Then after three, it decreased. And after three, it decreased again. This is where the shell changed. This is where the shell changed. But what about these two falls in the middle? And these falls were not that significant. Like the fall from one shell to another was big. For example, if you look over here, this one, you can see from 2370 to 519, that's a really big jump. The energy is much less, which means the shell is much bigger. The electron has suddenly gone very outwards, which is why it's easier to remove that. Similarly, from 2080 to 494, it shows that electron is much, much further away now, much easier to remove. But this change is not that significant. And this change is even not that significant. So they were baffled. They were like, ye baat puri nahi hui. And not just that. Further on, they saw that this change was bigger fall, and this change was smaller fall. And it happened in second period, it happened in the third period as well. So why does it work like that? They said that actually, even though this is the same level, this level is made of smaller levels. And those levels go like this: 2, 3, 3. But then they figure out that actually, every time there's a bigger jump, that is where the level changes. So this smaller level change is not because there's a new level being added or a sub level being added, because they called it a sub level. Sub level because it was within the same shell, but still just slightly bigger. So they said that it's not that it's like it is within the same level, but this change is not that big. So here's what they said. They said that, all right, this is the same level. Okay. But within that level, this is one small level, and this whole thing is one small level. And within that one small level, something is changing here. Now we can see that even though there is one level, there are two smaller levels in there. And then they found an idea. Obviously, I just have the data for first 11. If you look at the first 20, you will see that more clearly. Let me look it up. This is the second shell, and there are two sub-levels. And this is the first shell, and there was just one sub-level. And this is the third shell. And in the third shell, looking at the data, they did see that there were three sub-levels. Wait a minute, what's happening? Every level is made of the same number of levels as the level itself. So first level is made of one level. Second level is made of two sub-levels. Third level is made of three sub-levels. Fourth is made of four sub-levels. And so on and so forth. Interesting. And then one scientist, Pauly, had this idea that, wait a minute, it is not that they're basically coming out as two and then they're coming out as. So he saw, wait a minute, what's happening here? This number here, that is in the first sub-level, is one pair of electrons. And in the second sub-level, you have three pairs of electrons. So far we said that the levels are, there's the level 1, there's the level 2, there's the level 3. This level 1 is made of sub-levels, one sub-level, two sub-levels. So there's the one sub-level, first sub-level, second sub-level, first sub-level, second sub-level, third sub-level. And then he saw, wait a minute, it is not that we are seeing a jump after 3 electrons. We are seeing the jump because we are making 3 pairs of electrons. In the first one, there is one pair. So this is one pair and this is 3 pairs. And then when they looked at the third period, they did see that, wait a minute, in the first one, there was one pair. Then in the first one of the second, there was one pair. In the second one, there were 3 pairs. In the third one, there was one pair, 3 pairs, 5 pairs. And when they saw the fourth one, they expected and did get 1, 2, 3, 4 sub-levels. The first level with one pair, second level with 3 pairs, third level with 5 pairs, and fourth level with 7 pairs of electrons. And they were like, wow, there are so many patterns in there. And they were all coming from the ionization energy. So they were like, this pair thing has to have something. So they said, all right, let's call them, and this is the word that they gave it. Instead of calling them levels, they changed the word, they call them shells. This is subshell. And this one they called orbital because they couldn't call it orbit. So they said, actually, they're orbiting in pairs. And that is where Pauly made his biggest contribution to chemistry. He said that actually there is a pair because they're canceling each other's effect. Why was canceling important? Because here's the thing. We just said that they're orbiting, right? And if you remember O-level physics, you know that when charge moves, whenever charge moves, there is a magnetic effect. Whenever charge moves, there is a magnetic effect. And that magnetic effect, remember right hand grip rule or left hand grip rule? That magnetic effect is there and you can actually see it. It is very evident around us. For example, you take your phone or anything that has a magnet in there. You move it across any electronic thing, tabaa karke rakh doge usko. Because the magnet moving creates current. Just like that, a current moving also creates a magnetic effect. So he said that, wait a minute, these are electrons. They are moving around. If they were moving around, everything should be magnetic. So they are working as a pair because they're canceling each other's magnetic effects. He said that this magnetic effect or the pair thing, it's coming from the idea of spin. Spin is just in random words. They are not technically spinning. It's just a random word. And to take the spin idea, they said that in the orbital, there are one pair. So one is the clockwise spin and one is the anti-clockwise spin. Again, not true, not clockwise or anti-clockwise in the sense that we think it is. Just a random thing. Electron asal mein clockwise घूम नहीं रहा होता. Just a name that we've given it. Makes sense. And this is where that small jump within the same sub-level came in. He said that basically these 3 pairs showed this fall. This fall was because the first 3 are not pairing up, but the next 3 are pairing up. So when you add that pair, it makes it easier to remove them as well. They're more stable as individual, but as a pair, they're not that stable until you complete the effects. So this small jump is not because of sub-level or something. It is because of the spin pair repulsion. And there you go. Within the level, there are 3 further divisions, and that explains the 3 jumps. From one shell to another, there's one big jump. Within the same level, there are, for the second level, there are one big jump because there are 2 sub-levels. For the third level, there are 2 big jumps because there are 3 sub-levels. For the fourth level, there are 3 big jumps because there are 4 sub-levels. And within the same sub-level, you will see a jump. In the first one, it comes after the first pair. In the second one, it comes after the third electron, because you're taking the pairs. In the third sub-level, it comes because of when you add the 5th electron, because you're making 5 pairs. In the fourth one, it comes because of the 7th electron, because you're getting 7 pairs. And that is how you get the model of where the electrons are. So let's bring it all back. Let's summarize this. रैशनल समझ आ गया सबको कि कहां से ये लेवल्स आते हैं, कहां से सब शेल आते हैं, ये 4 डिवीजन्स क्यों हैं, स्पिन क्या है, the thought process. Do you all get it? It's important that you do.
Sir, I think I understand.
So now we're going to give them names, because again, this is O levels. We are trying to keep things simple. So this shell, we are going to just give them the numbers 1, 2, 3, 4. The subshells, instead of naming them this, we are going to give them a name, S. The second one will have S and P. Third one will have SPD. Fourth one will have SPDF. Can you guess what about the fifth one? Go on. ज़्यादा से ज़्यादा क्या होगा? खराब हो जाएगा, गलत हो जाएगा. There's no embarrassment in that.
Sir, what's your question? Sorry.
My question is, if the fourth one has SPDF, what will the fifth one have?
No idea, sir.
Why not? Fourth one, fifth one will have. Yeah, go on.
SPD. I think double S and then PD. I don't know.
No. There is no double S. SPDF, and the next one?
Will again be S or F?
G. Alphabets. SPDFG. Next one will be FPDFGH.
Sir, but isn't our syllabus just like restricted to the F orbital? I'm not sure, but
you know there is a reason for that. If you do go out and find G, you will be the first human to do that, because nobody has ever found an atom big enough to have G in there.
But like people have named it G without it existing.
No, we do know it exists. We just haven't found it. Like, we're pretty convinced our theory works. Okay, now there are orbitals, and orbitals are, then they did some scanning and all that, some of which we will see in A2. And they found that orbital is actually the first place where electron is. This is not a place, this is energy. This is not a place, this is energy. But orbital is actually a place. It's the first, it is the place where the electron is. ये उसका घर है. And this is the first orbital. दूसरे वाले में एक ऑर्बिटल है, तीसरे वाले में 3 ऑर्बिटल हैं, फिर एक ऑर्बिटल है, 3 ऑर्बिटल हैं, 5 ऑर्बिटल हैं. तो D में 5 orbitals हैं. D has 5 rooms where it can accommodate these electrons. And every room has a bunk bed. There is a pair of electrons that can come in there. तो वो जो इलेक्ट्रॉन है वो इस पेयर के अंदर आता है, ये पेयर उसके अंदर आ जाते हैं. Okay? So basically, now we are going to fill electrons based on that. So now we know, just to summarize this, what's the division? Starting with the very lowest level, when electrons are going to be filled up, they fill based on the off-bar principle. Off-bar principle says, जो काम सस्ते में हो रहा है वो महंगे में नहीं करना. अगर एनर्जी कम लग रही है, काम हो रहा है, तो why go for the higher level? That's what electrons do. They build energies up. So build energies up. Which means if the lower level is empty, electron will go there. Okay. Next, electrons. This is Pauli's exclusion principle. This is one of the reasons he got a Nobel Prize. Pauli was a crook, by the way. I personally don't like him that much. People have said that he stole his ideas from his students. So Pauli's exclusion principle basically says that no two electrons in the atom can have all four states as equal और identical. अब फोर स्टेट्स क्या हैं? किसी भी इलेक्ट्रॉन की फोर स्टेट्स होती हैं. वो फोर स्टेट्स क्या हैं? उसका शेल, सब शेल, orbital, spin. These are the four things you need to know about every electron when it goes into the atom. So shell is the very first level. Within the shell, there is subshell. Within the subshell, there is orbital. Within the orbital, it can spin up. So there is the up spin or down spin or clockwise or anti-clockwise spin. Okay. How do the energies rise? Of a principal को अगर हम देखें, energies rise like this. So you start with 1, 2, 3, 4. इतना काफी है अभी के लिए. This is energy increasing. Okay. First is the lowest energy. Fourth is the highest energy. Okay. 1 has S. Obviously, 1 has just one subshell. 2 has two subshells, so S and P. 3 has three subshells, S, P, D. 4 has four subshells, S, P, D, F. Okay. Now, how do energies increase? Number one, another important thing, energy levels or energy shells are discrete. Do you understand discrete? Discrete is like you were in O3 last year, right? And then you got your result and now you're in A1. There wasn't a transition there. One moment you're in O3, the next moment you're in A1. There wasn't an O3 and a quarter or something. You just jump directly from one to another. That's what electrons do. They go from first to second to third and fourth. They can't be in 1.5 or 2 3/4 or something. Okay? So discrete like that. Then they always do off bar. They fill it from lower to higher. And how do they fill it? Let's look at that. The first one to fill, we are going to draw these slant lines. So the first one to cancel is 1s. So that's the lowest energy level. Second one to cancel, I'm going to copy this one. And second one to cancel is 2s. So 2s is the second one. That's the one that has the next highest energy. Then I'm going to get the third one. Third one goes like this. There is the first to cancel is 2p, then 3s. Then I have the fourth one, p, 3p, 4s. Interesting. This is interesting because I still have 3d to go, but I did not cancel that first. And that comes from actual experimental evidence that when you do the next one, you're not going to get 4p or something. You're actually going to get 3d, 4p, 5s. And that's how it goes. 3d, 4p, 5s. But in AS, we're going to stop here. So one thing you have to remember, 4s has lower energy than 3d. This is a key point to remember. So they go like this, S, P, D, F. But 1s, 2s, 2p, 3s, 3p, 4s. Not 3d. Because when they're empty, D has higher energy than 4s. This is a key point to remember. Okay, they feel like that. Within each one of them, there is orbital. S has one orbital. So S has one orbital. We're going to show it with one box. P has three orbitals. So we're going to show it like that. D has 5 orbitals. And F, as you can guess, it has 7 orbitals. And these are odd numbers, by the way. 1, 3, 5, 7. They have odd number of orbitals for some reason. We will talk about why that is the way. अब हम देखते हैं कि S की शेप भी होती है, बिकॉज आई टोल्ड यू S इज अ फिजिकल प्लेस. सो S इज अ स्फेयर. S for sphere. So when you actually look at the electron, where is it? It's in the sphere. What about P? P is, I don't know why they call it P. There was a word for it something. But P is 3 because P is actually for X, Y, and Z directions. So there is one P that is, this is X, Y, and Z axis ना. ठीक है, मैं इसको copy कर रहा हूँ. So the first one is actually like this. कि वो इसके यहाँ पे होता है इलेक्ट्रॉन, उसकी शेप ऐसे करके होती है, और इस साइड पे होता है इलेक्ट्रॉन. This shaded area is anywhere electron can be. And then there is the other one. और इसमें क्या होता है कि आपका इलेक्ट्रॉन जब आपको उसको ढूंढते हैं ना एक्स-रे क्रिस्टलोग्राफी वगैरह से, तो इलेक्ट्रॉन यहाँ पे होता है या यहाँ पे होता है. और जब हम तीसरे को देखते हैं तो इलेक्ट्रॉन यहाँ पे होता है या यहाँ पे होता है. And they are, interestingly, they're along the 3 axes. कि that is the place where you can find electron. इलेक्ट्रॉन कोशिश करता है कि वो या तो एक्स एक्सिस के आसपास घूमता रहे, या वाई के आसपास घूमता रहे, या जी के आसपास घूमता रहे, और आपस में उनका एंगल 90 का है. एंगल मैटर कर रहा है. क्यों? क्योंकि वो रिपेल कर रहा है, वो एक दूसरे को आने नहीं देते अपने एरियाज में. एंड दिस शेप वी कॉल इट अ लोब. इसको हम ड्रॉ करते हैं ऐसे, स्फीयर को हम ड्रॉ करते हैं ऐसे. अब हम आ जाते हैं डी पे. हाउ मेनी ऑफ यू आर नॉट प्लानिंग टू डू A2? आर यू प्लानिंग टू डू A2?
What do you mean?
लाइक A1 के बाद A2 करना है या नहीं करना?
हाँ, मतलब सर ये
option?
करना है.
No, if you are planning to go to US or Canada, you don't need A2. So ये सिर्फ पाकिस्तान और जहाँ जहाँ इंग्लिश सिस्टम है उनको जरूरत है A2 की. Nobody really needs A2. बहुत कॉम्प्लेक्स होता है वो. Anyways, so if you are planning to do A2, so this will help. कि D is like a butterfly. And D में क्या होता है कि आपके पास इस तरह का केस होता है. It is like this, 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 and this. And then there's another one which is like this, 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 and this. बेसिकली क्या हो रहा है यहाँ पे, ये अभी आपको समझ नहीं आ रहा होगा. उसकी वजह ये कि टू मेक इट मोर विजुअली अंडरस्टैंडेबल, आई विल जस्ट ड्रॉ 2 शेल्स नाउ. सो दिस इज x एंड y, और ये y और x के बीच में है. और फिर इसी तरह आई हैव x एंड z, और ये x और z के बीच में एक बटरफ्लाई सी बनी हुई है, which is where you can find the electron. अगर आप उसको ढूंढने निकलेंगे तो there is high probability you'll find it here. And there's another one which is between, as you can guess, y and z. और y और z के बीच में इलेक्ट्रॉन है. And then ये तीनों between the axis है ना. फिर हमारे पास 2 along the axis भी होते हैं. ठीक है, और वो इस तरह से हैं कि हमारे पास ये पहले 3 समझ आए. They're between the 2 axes, x और y के बीच में, और y और उसके बीच में, and all that. And then there is another one which is, this is x, this is y, and this is इसको हम y कह देते हैं, इसको z कह देते हैं. And there's another one that is like this. The butterfly is along the axis, just like p, but ये p का डबल हो गया एक तरह से. And then there is another one which is like this, but it's interesting to know कि वो ऐसे घूमता भी है. So there is 2 that are along the axis. So वो odd क्यों है? क्योंकि 3 एक्सिस है आपके पास, तो वो अपने आप को उन एक्सिस में फिट करना चाह रहे हैं. इसको हम कहेंगे कि ये x के साथ है तो ये px है, ये y के साथ है तो ये py है, ये z के साथ है तो ये pz है। ये x और y के बीच में है तो इसको हम कहेंगे dxy, ये x और z के बीच में है तो इसको हम कहेंगे dxz, ये y और z के बीच में है इसको हम कहेंगे dyz, और ये वाला उनके ऊपर बैठ के तो हम कहेंगे कि ये x के ऊपर भी हैं दोनों और y के ऊपर भी हैं दोनों, और ये वाला z के इर्द गिर्द घूम ही जा रहा है। सो दिस इज d स्क्वायर्ड, dz स्क्वायर्ड। तो हमारे पास ये क्या,
जी से बस ये यहाँ एक मिनट।
सो द स्फीयर इज एनीवेयर अराउंड द न्यूक्लियस। तो न्यूक्लियस आपका यहाँ पे एक्स वाई जी तीनों को वो घूम रहा है, कोई फर्क नहीं पड़ रहा उसको। एंड दिस इज वेयर द इलेक्ट्रॉन लिव्स। सो जो बचपन में सर्कल देखे थे वो मजाक था, वो सिंप्लीफाई किया हुआ था जैसे इरा ने कल कहा था। नाउ वी नो वेयर इलेक्ट्रॉन इज, वी नो इलेक्ट्रॉन मस्ट पेयर अप टू कैंसिल ईच अदर्स magnetic effects and all that, and these are the places, these are the bunk beds that they have. कल हम देखेंगे कि हम इसमें इलेक्ट्रॉन को अब अकोमोडेट करेंगे। We will push the electrons in there based on their energy levels and try to figure out, can we look at the table of data just like the scientists did and figure out where the electron is and what makes it go in one bed or the other. Okay, or one room and the other. Okay, any questions?
So the last one for D is called dz squared.
Yep.
I don't get this. These shapes जो भी आपने बनाई हैं.
The real reason of why the shapes are the way they are I think 3 और साल केमिस्ट्री पढ़ेंगे तो समझ आएगी, या चलें 2 और साल तो एटलीस्ट पढ़ें, नहीं 3 करें। That's one problem we have, इसलिए हमें शेप्स को बस याद करना है।
Okay, sir.
All right.